In the previous episode, we saw Kroneker's generalization of Dirichlet's theorem on primes in arithmetic progression. In this episode, we're gonna look at an even more general formulation of this by Weber. For this formulation, Weber generalized the concept of ideal class group as well as that of the group Z mod MZ star. He defined generalized ideal class group, and in this terminology, Dirichlet's theorem just become a statement about the size of the ideal class group. When K is Q and L is the M cyclotomic field over Q, if we let H be the set of primes of K that's split over L, which in our case here is just a set of primes P congruent to 1 modulo M, then in that case, Weber's theorem says that the index of H inside this group IM, which we'll define later, it's going to be equal to the degree of this extension here. In particular, this implies that there are infinitely many primes in each coset of this generalized ideal class group, which in this case is just going to be isomorphic to the unit group of Z mod MZ. And that is exactly the statement of Dirichlet's theorem on primes in arithmetic progression. So, what are these generalized ideal class group? As this is a generalization of the ideal class group, the generalized ideal class group is also gonna be the quotient of some group of fractional ideals over the quotient of some group of principal fractional ideals. The difference is that we're not gonna necessarily concern ourselves with the group of all fractional ideals. We are only gonna be interested in fractional ideals relatively prime to a given modulus M. So what's a modulus? Well, for Weber, a modulus is just a non-zero ideal of OK. Later, we're gonna discuss Takagi's notion of modulus, which will allow also infinite primes. But for now, let us just use Weber's definition and think of every modulus as a non-zero ideal of OK. Given such a modulus M, we then define IM to be the group of fractional ideals relatively prime to M. And then instead of looking at all principal fractional ideals, we're gonna only look at those which are represented by totally positive elements that are congruent to 1 modulo M. So let us explain what that means. First, to say that alpha over beta is congruent to 1 modulo M means that alpha, beta are elements in OK relatively prime to M, and their alpha is congruent to beta modulo M. Next, to say that alpha over beta is totally positive means that their image under every real embedding of K is gonna be a positive real number. So that was a little bit abstract. Let us now look at some examples of this P plus M to get some intuition. Now if we pick M to be 1, then the condition that alpha over beta is congruent to 1 mod M is trivially satisfied. Thus, P plus 1 is just a group of principal fractional ideals generated by some totally positive quotient of elements in OK. So let's look at some example. Let's say K is Q joined square root of 2, and I is just the principal ideal generated by square root of 2. Now the question is, does I lie inside P plus of 1? In other words, does I have a generator that is totally positive? Its image under all real embedding of K is positive. Well, to figure that out, we must first determine what are the real embeddings of K. Now, since square root of 2 is a primitive element of K over Q, the real embeddings of K are just all determined by where they stand square root of 2, and we have two real embeddings. One is the identity, and the other one sends square root of 2 to its conjugate, namely negative square root of 2. From this, we immediately see that square root of 2 is not totally positive because its image under this sigma is negative. So then, does this mean that I is not in P plus 1? Well, not quite, because if you look carefully, the condition for I to lie in P plus 1 is that I has some generator that is totally positive. It didn't require that all generators of I be totally positive. So even though square root of 2 is not totally positive, I is still gonna lie inside P plus 1 because I has a totally positive generator, namely square root of 2 multiplied with 1 plus square root of 2. So how did we know to pick this generator? Well, every generator of I is going to be an associate of square root of 2, right? Which means that it's going to be the product of square root of 2 with some unit. Now, square root of 2 has norm minus 2, and this unit has norm minus 1. So this whole product has norm 2, which is positive. Thus, the conjugate of this product must be a positive number. And note that the conjugate of this product is just the image of this product under this sigma map here. So we see that this product is totally positive, and thus I has a totally positive generator. This means that I lie inside P plus 1 as claimed. Now let us look at an example of an ideal that does not lie inside P plus 1. If we let K be Q adjoint square root of 3 and let I be the ideal generated by square root of 3, then we claim that I is not gonna lie inside P plus 1. i.e. I cannot have any totally positive generator. So let's see why that is. Now observe that any generator of I must be of the form square root of 3 multiplied with some units in the ring of integer of K. If we take the norm of such an element, we see that the norm of square root of 3 is going to be minus 3. Whereas the norm of a unit in the ring of integer of Q adjoint square root of 3 is going to be equal to 1. So the norm of this product, the norm of this generator here, is going to be negative. So this generator here cannot be totally positive because the norm is just going to be the product of the conjugates of this generator. Thus, as the norm is negative, one of the conjugate of this generator must be negative, and so this generator cannot be totally positive. Thus, that's an example of an ideal that does not lie in P plus 1. So those are some examples of ideals lying inside P plus M. Now that we have defined Im and P plus M, up next we're going to define the notion of generalized ideal class group. And then we're going to talk about how Weber used this notion of generalized ideal class group to generalize Dirichlet's theorem on primes in arithmetic progression.